delegates to take their respective seats, and we begin with the function. I would like to request each one of you to please keep your phones on silent till we conclude with the function. I request Chairperson NCRF, Professor Dr. Alpana Goyal, Honorary Chair NCRS Professor Dr. P.V. Varde to welcome our Chief Guest, Dr. D.K. Aswal, Group Director, BARC, with a Tulsi sapling. Thank you, ma'am. Thank you, sir. I request the chairpersons to kindly welcome our guest of honor, Professor Dr. Umashankari Kannan, with the Tulsi sapling. I also request the chairs to please welcome Dr. W. Selvamurthy, President, Amity Science, Technology and Innovation Foundation. I thank all the dignitaries who have graced this occasion with their benign presence. To formally commence the proceedings, I now invite Professor Dr. Alpana Goyal, Chairperson NCRS 2025, Director and Head AINST, to kindly deliver the welcome address and opening remarks. Ma'am, please.
Good morning, all. Respected dignitaries sitting on the dais and off the dais. It is my distinct honor and privilege to extend a warm welcome to all esteemed guests, delegates, and participants present here today. On behalf of Amity University, Uttar Pradesh, I am delighted to welcome you to the National Conference on Reliability and Safety at NCRS 25, organized in collaboration with the Society for Reliability and Safety, SISA, at our Noida campus. Over the course of the next 2 days, on March 20th and 21st, we look forward to insightful discussion and valuable learning experiences as the theme of the conference emphasizes the critical importance of reliability and safety in various sectors. This conference is proudly supported by Atomic Energy Regulatory Board, AERB Mumbai, along with the several key players from the nuclear industries. I am deeply honored to welcome our chief guest, Dr. D.K. Aswal, Group Director, Health, Safety and Environmental Group, Associate Director, Medical Group, and Director, National Radiation Emergency Response, BARC, Mumbai. Dr. Aswal's remarkable contribution to the nuclear field, coupled with his unwavering commitment to raise the awareness about nuclear energy, and have left an incredible remark on the scientific community. His ability to communicate complex ideas in a simple language makes him an exceptional speaker. If we have more scientists like him, I am 100% sure that India will soon become a self-reliant, dependent country. His ability to communicate complex item, as I have already shared with you, and I got many times opportunity to listen to him, and even today and anytime I don't want to miss his talk. So that is a motivation for all of us. And sir, we are honored to have you here today and our sincere thanks to you for gracing us with your presence. I extend a warm welcome to our guest of honor, Dr. Uma Shankari Kannan, former head Reactor Physics and Design Division, BARC. Dr. Kannan has had a long-standing association with AINST students and faculty members. He actively guided our BTech students and PhD scholars. Her invaluable mentorship has been pivotal in shaping our academic activity. Thank you, ma'am, for accepting our invitation. I would like to welcome Dr. W. Silvamurthy, President, Amity Science, Technology and Innovation Foundation. His unwavering mentorship and guidance have played a crucial role in shaping the journey of AINST. Thank you, sir, for all your continuous support. Thank you and coming here. Now, I would like to welcome all dignitaries sitting here, from the head of the institution, head of the department, senior faculty officials from Amity University, and they have joined online and offline. Your participation enriches this conference immensely. I would like to extend my gratitude to our invited speakers, Dr. D. Datta, Dr. M. Sai Baba, Dr. S. K. Gupta, Dr. R. K. Sharma, Dr. Dharam Raja, and along with all contributory speakers and registered participant and his student. Most importantly, the student and the student who are from the school. So I welcome you all here. A special welcome to our industry partner from AERB, from Advanced Tech, from Thermo Fisher, from ACDS, from Sharu Metals, Ortec, Amitech, Aramec, OCEM India. Without your support, it won't be possible for us to organize this conference. So thank you for your collaboration and support. Lastly, I would like to acknowledge the significant contribution of my co-partner in organizing this conference, Dr. P.V. Varde, President of the Society for Reliability and Safety. Your guidance and support have been integral part for making this conference a reality. I extend my heartfelt welcome to each one of you, and I am confident that this conference will provide a platform for enriching discussion, knowledge sharing, meaningful collaboration. Together, let us work towards enhancing the understanding and implementation of reliability and safety principles, ultimately contributing to safer and more efficient system across various industries. With this word, I conclude my remark, and I hope everyone will be getting 2 days will be very hectic. You are going to hear the lot of talks which are on reliability and safety. This is very, very important topic, especially when we work in the nuclear industry. With this, I give the best wishes for the success of the conference. Thank you.
Thank you, ma'am, for your inspiring words and setting the tone for today's event. It's now my privilege to invite Professor Dr. P.V. Varde, Chief Executive and Managing Director, ERAMC, former Associate Director, Reactor Group, BARC, Mumbai, to deliver the presidential address. Sir, please.
Dignitaries sitting at the dais and amongst the audience. my dear students, faculties, ladies and gentlemen. Indeed, it is an honor to give a presidential talk at this sixth NCRS. And we can see the history of National Conference on Reliability and Safety. In any society, this is a paradox of SRESA, which was established in 2010, and now it is completing almost 15 years. So it is you start with the workshop, national conference, international conference, and then further events, ambitious events. But for SRESA, the story was a little different in the sense that we started with an international conference on reliability, safety, and hazard. And this product of SRESA, it is called iCrash. So once first iCrash, that is 2005, when it was done, it was realized that we have a need of society, because the kind of response that we got in this iCrash 2005, and the kind of developments which were going on in various units of not only Department of Atomic Energy, even in various universities. So we were motivated to do the NCRS, and finally we established this NCRS. So NCRS came into existence quite late, somewhere in 2014, while we did our first iCrash event in 2005 only. Now, the 5 iCrash events, one in Sweden, 4 in Mumbai, and 1 in Chennai. Let me tell you, even though it is reliability and safety being the abstract sort of, if you see in outside or generic domain, the kind of response we would get, it was enormous, whether it is exhibition, whether it is, talks that are coming in, and kind of foreign participation. In the first conference itself, we had almost like 40 foreign participants, and all of them are expert in the field. So this kind of thing, and then I feel personally that any conference, its soul is its proceedings. So you see the trend. Many conferences, they will wind up with the abstract book, and that's the end of it. But here we have been publishing all our books, our proceedings, through Springer. That means at the local level, yes, people who attend the conference, but at international, it has got a wider participation in visibility. So, having talked about 5 iCrash event and NCRS, then the next more ambitious project was to bring out the standards, code standards and guide. This was a very tricky task because, our first standard, which was in for a nuclear power plant, the topic was probabilistic risk assessment. And I think standard was developed, but then it was to be published through Bureau of Indian Standard, BIS. And now we are going through the process, and I am happy to inform you that maybe in 1 month or 2 months, it will be published as a this national standard actually, So of course ARB had their own reservation, DAE had that, but then finally everybody agreed that this standard should be there actually in the. After that, if I come to one important project that SRESA had, it was an International Journal of Reliability, Safety and Life Cycle Reliability and Safety Engineering. When this journal was launched, I was not confident that it will survive. In fact, Dr. Anil Kakotkar, it told me very clearly, Dr. Vardhe, it is very easy to bring out a journal, but it is very difficult to sustain it. That was his remark, I remember. And I told him, sir, we have a strategy. We make the proceedings or that, issue, 6 months before. And that's why we have the confidence that we will do it. Fine, whatever. But now it is almost like 13 years. This journal is there in the public domain. It has got its reach in, I think, 15 to 20 countries. And we got the Scopus. And Scopus is a very important milestone because then you keep getting more papers from at national and international level. So And now, maybe in a couple of days or maybe month, we will be getting this impact factor. And once you have impact factor, then I think there is no looking back. And then, when the society grows, in fact, myself was one of the founder for this society. And then one gentleman sitting here, Professor S.K. Gupta, sir, one of our seniors, sir, you can say bye to all of us, Gupta, sir, he's sitting there. He was our first president and I was first secretary. Okay. And we started the society in 2010. Now, when I talk about how your ambition increases, general conference, this thing, and then we thought, why not we go for institute, having our own institute. So last 2 years, the work is, let me admit, it is a very ambitious project. 2,000 crore is the all, I can say even impossible also. So we are working on Indian Institute of Risk and Reliability, and probably it will take time to mature on this actually. Now, the way ICRESH is very close to my heart. NCRS is, because NCRS was our venture at the national level. ICRESH happens every 5 years. In between, there is a lot of gap. So people advise us, why don't you do annually this national conferences so that, our synergy will be there all across the country. So this, we are NCRS 6. That means it has become self-sustaining now. What is happening now? I got the invitation to do next NCRS in Hyderabad DRDO. So this is how earlier we used to go and request people, please organize this event. Now people come to us to organize either ICRESH or SRISA. This is how I call sustainability actually, So now we are into NCRS, and my feeling over the year, for me, young generation, faculties, student, they are very important. Seniors have done whatever they have contributed to the nation and all, but students are very important. And my one comment I reserve, and today I'm coming with you is, this is something I will talk in my BRC tennis school or in Maryland also in the class, that when my student and I'm giving the lecture, a symphony should come out. This is an interaction going on, a music should come out. If the music doesn't come out, then it was a mechanical thing which was existing. And music should come out in a sense that not only at the level of brain, it should work at the level of self. So individuals are, getting ready to work in their field. And I'm telling, especially to my students and young generation faculties and all scholars, that please take full advantage of NCRS 6. The Amity team under the guidance of Goyal Madam, and of course, I've been interacting with Archana also. So they have worked very hard. So take every bit of it. There are a lot of takeaways. Live every moment, dedicate your time, and there's a lot of things to learn. And what was quality in 60s? Quality, Japan's, way of working. Now it is reliability and safety. If your product, I've seen many products, they are lying and there is no user because somebody buys it and they are not performing in the field. This is 90% story. Startups are failing. In fact, I have also started my own startup. So now let me see how it works, whether I am able to meet that, difficult standards actually. So the issue is, if the reliability and safety standards are not met, then probably quality, of course, even today it is there, but it should be having a reliable, and India is entering into the club of advanced countries. Maybe it is a matter of time, and that will happen. This will be one of the things: sustainability through reliability and safety. That is going to be the thing there. As far as so for students, the message is clear: take full advantage of it. As far as the visibility of SLESA, there are 6 chapters all across India we have set up. Of course, here I have to work a little bit. That kind of synergy we have to bring in, and we are creating a future for you. Please take advantage and learn from here. And same synergy should happen at the industrial level. It is already there, but that is a real enhancement is required. So with this, I would say thank you very much for giving me this opportunity. Thank you, the organizing team, for having me here as a for presidential address. Thank you.
Thank you, sir, for sharing your valuable insights. We are honored to have amongst us Dr. W. Selvamurthy, President, Amity Science Technology Innovation Foundation. Sir has had a meritorious career and became the director of two DRDO institutes, Defense Institute of Physiology and Allied Sciences and Defense Institute of Psychological Research during his 40 years of service in DRDO. And he has been presently working with Amity University as the president of ASTIF. He is also the Director General for Amity Directorate of Science and Innovation. He is a distinguished scientist and served as Chief Controller, Research and Development at Defense Research and Development Organization, Government of India. Sir, I please request you for your address.
I speak from here. So very good to every one of you. Very distinguished guests, and the dais, after dais, and all the very distinguished participants, particularly my students from Amity International Schools, and welcome to this very important event, which is organized by Amity Institute of Nuclear Science and Technology. On behalf of Founder President, Dr. Ashok Chauhan, the Chancellor, Dr. Atul Chauhan, and on behalf of everyone in the Amity family, I have great pleasure in welcoming all the very distinguished guests who have come to grace the occasion, address all of you over here, and also share their thoughts and also some way ahead. Margdarshan dene ke liye aaye. So I welcome each and every one of you. Dr. Aswal, he is known to me for a very long time, since my DRDO days. And also as the director of NPL, we used to visit there during his term. Amity relationship, collaboration, interaction with National Physical Laboratory was very strong. In fact, founder president Dr. Ashok Chauhan himself used to visit this institute, and meteorology and many domains in which we collaborated. And he is now playing a very important role in BORC, and he is the group director of Health, Safety and Environment in Baba Atomic Research Center. So such a very distinguished person. And he has made a mark in the atomic energy through his contribution in the area in which you are going to deliberate during the next 2 days. So welcome, Dr. Aswal, for this, and being the chief guest, we are delighted to have you over here. We're also fortunate to have Dr. Uma Shankari Kannan. I just had a very brief interaction. And in fact, she has also served at the Atomic Energy, Department of Atomic Energy, BARC, for a very, very long time. And then she was the former head of reactor physics and retired very recently. And then also design division. These two are very important. Because any equipment, any system of systems design, it starts with the design. So she had the opportunity of heading that, and also reactor physics. All the reactors, the basic fundamental life is the physical principles. So she has been looking at the research and development endeavors related to reactor physics. Welcome, madam, and she is the guest of honor today, Dr. Uma Shankari Kannan. Welcome to Amity. And we're also fortunate to have Dr. Vardo, and we just listened to him. And he is the president of that very important society. And he has promoted the activities in such a way that he has given outstanding leadership for the society. And we will work with you, and certainly Amity will be glad to associate with you. And we're also very fortunate to have very distinguished speakers, guests, like Dr. S.K. Gupta, the veteran scientist. I think he is here, yes. And Dr. Sai Baba, whom I have met, interacted several times. We like to see that how we associate. He is in the National Institute of Advanced Studies, which is one of the apex body and think tank, which looks into the way ahead in terms of strategies, policies, And he has also been associated with IG card for a very long time. So, which is a very important lab in Chennai, which deals with all the sensor development and many, many activities related to the technology development for atomic energy. Then we are also fortunate to have Dr. Datta, Dr. Roja, and all the very distinguished people who have come to grace the occasion, including Dr. Prakash Kumar Sharma, Dr. Dhanraju from IIT Delhi, who is here. And so, welcome to each and every one of you. Above all, our Amity International School, which is, looked after by Dr. Mrs. Amita Chauhan, and she has deputed so many students. I'm so happy because they are the future. So we are investing in the future. Thank you, madam, for deputing these people. Because we cultivate the research and innovation culture not only in university and higher education, but we do that in the school. Even in the preparatory schools, we have AMION. We have 5 of the preparatory schools, 28 schools. We have primary and secondary schools. We have 12 universities in India, 18 campuses abroad, 28 schools. 250,000 students, 10,000 faculties, 5,000 PhD scholars. So this is what is Amity today, Amity Universe. And this is founded by Dr. Ashok Chauhan, and the schools are being looked after by Dr. Mrs. Amita Chauhan and his own family, his sons and daughters-in-law. Everyone looks after Amity whole group. That is how it has grown. And we also have people like you blessing the organization to grow. So thank you so much for your gracious presence here. Let's welcome our distinguished guest with a big applause. I also appreciate Dr. Alpana Goyal, one of our distinguished faculties, who is heading the Amity Institute of Nuclear Science and Technology. See, Dr. Chauhan is a visionary. Why we call him a visionary? When the university started in 2005, Amity University, this Noida campus was the first one, and he thought of areas like space science and technology at that time, nuclear science and technology, now defense technology, Amity Institute of Defense Technology. So like that, no, that is why we call him visionary. And he thought of all this, and nuclear science and technology is one of the premier institute in Amity Group. And Alpana Goyal is, we are fortunate to have such a great leader with us. And she has brought a very big international project from US Department of Defense, United States, Defense Threat Reduction Agency on nuclear security, safety, all these aspects she deals with. And she also is closely associated with International Atomic Energy Agency. So such distinguished faculties head our institution. Let's clap. And also Dr. Archana Yadav, she is going to be soon Dr. Archana. I will call her Miss Archana Yadav, who is now comparing as well as the spearheading this activity along with all the distinguished Arpita and all the distinguished faculties. So my appreciation to you, Alpana, with your team for this organizing this very important event. Let me say a few words about your founder president who has created this whole Amity universe. He himself is a PhD in the chemical engineering. He did chemistry and then did, in Germany, he did his doctorate, and he was there for almost 28 years, more than 28 years, and became as a very powerful non-European investor in Germany. And then when he came back to India, when the reunion took place, he was the largest non-European investor in Germany. Then he invested all his learnings, earnings, everything in education, research, innovation, and philanthropy. That is how the whole Amity universe has come. And so a salutation to our founder. And also about Amity Universe, I'll say a few words because that is the host which is organizing this. See, we are making all the institutions research and innovation driven university. So the curriculum design, pedagogy, the method of delivery, everything is based on promoting creativity, innovation, problem solving ability. That is what we give it to our children. Because Amity is in a mission to churn out the future global citizens who are endowed with knowledge, including spiritual knowledge, skills, including soft skills, good behavior, sanskars, values, resilience to face challenges like, the mission which we had, the space mission, yesterday, Sunita Williams coming back, resilience, which is very important for survival as well as for the success in life. So such things we give it to our children. So that is the mission of Amity Universe. And Amity today is conducting 500 research projects funded by national, international funding agencies, including DETRA, which is $1.2 million investment. And we have projects from NIH, Wellcome Trust, and also the DSTD, BTI, CMR, ICAR, DAE, BRNS, and also ISRO. Now the respond call recently, we have applied 115 projects, proposals. So this is Amity. We have so many projects, and the value is about 300 crores ongoing projects. Then we have published 45,000 research papers in journals of repute, and our H index is 172 today. And then we have filed 2,350 patents, which has been filed, 500 patents granted, which are now being translated into technologies, products, processes. And we have transferred 35 technologies to the industry. And we are promoting startups. We have a very strong incubator, which has produced more than 1,000 startups. So you should visit sometime when you are here. Please do visit us. And so we have a Amity Venture Capital. We have, if you have a brilliant idea, we have a venture capital. So this is Amity Universe. So we are, depending on the attitude, aptitude of the students, we promote whether they will go for placement or a job, or they will become an entrepreneur, they will give a startup, or they will have a venture support. So we decide students as per this and their devotion, passion, junoon. So we look at this and promote this. This is Amity. Then coming to Amity Institute of Nuclear Science and Technology, which is one of the important institute, we churn out the future leaders in nuclear science and technology. So when Dr. Sinha visited, she looked at this. This is the first institute of nuclear science and technology. And we are giving degree programs, postgraduate and doctoral program in nuclear science and technology. So this was started here, and we churn out the human resource. The next thing is we do research. We do a lot of research related to nuclear safety, nuclear security. So how do we secure our nuclear assets, not only in the military or defense security platforms, but how do we secure these assets in the civilian sector? Because there are so many nuclear sources, cobalt-60, CCM, isotopes, everything is there in the hospitals and food irradiation. So how do you secure these assets? Nuclear security. This is what is the focus today by the DETRA project which we are doing. So this is what is the mission. Now coming to the team, DRDO, when I served at DRDO for 40 years. So we had a separate directorate of quality, reliability and safety. There is a separate directorate because we develop military platforms like missiles, Agni, Prithvi, Akash, Nag, Trishul, BrahMos, interceptor missile, and so many asset that is anti-satellite missile. So like this we develop. So where quality is important, reliability important. When it has to fire for a second strike, you have to fire. It has to be 100% reliable. So the reliability in any system, whether it's missile, aircrafts, the fourth generation plus aircraft Tejas, or main battle tank Arjun, or it is nuclear powered submarine, the Arihant. So everywhere, the first is quality and then safety and also reliability. So these are the important things in a weapon platform or even in equipment which you handle every day. Whether it's a camera or a mic, it has to be reliable and it has to be safe. It should not give me a shock. So these are all aspects which comes in every spheres, whether it is reliability and safety. So it is just not only for atomic energy or defense, but it is there in every sphere of life. So it should become a culture. It is not just only a practice for equipment development. It should be your culture. You should be reliable. Your every process should be reliable. And it should be safe. So that is why this theme of this conference is important, reliability and safety. And atomic energy is much more important because you are dealing with very high nuclear reactors. So the safety has to be ensured. So they have several layers of safety put in that. And then every equipment they develop, every source, radiation source they develop has to be safe, reliable. So this is what is the atomic energy. And Dr. Oswald comes from, and many of them come from that great organization, Atomic Energy, we are proud of. So only the radioisotopes which is being given, the AERB looking into safety, But then this atomic energy is also looking into nuclear power submarine, where the heart of the nuclear power submarine comes from atomic energy. Similarly, when you look at nuclear missiles, are the Pokhran 2 is all atomic energy and DRDO together. So that is why this organization is very critical, strategic, as well as very important in every sector of our life. And thank you so much for so many very distinguished people from BARC Atomic Energy are over here. And some of the budding scientists who will be joining this organization are also over here. Now, coming to the message, carry home. The first thing is, Honorable Prime Minister has given the vision for the nation. That is Viksit Bharat. By in the next 20 years or 22 years, you should become a developed nation. When we celebrate the 100th year of independence, we should be a developed country. So how do we ensure this? In every sphere, the 5 verticals, 5 pillars, you know about this, but everywhere, reliability and safety has to be there. So that is what I would like to relate, not only for atomic energy or space or it is the DRDO, but it is there in every sphere, reliability and safety. And Amity is contributing in a big way in this. So we like to participate in this mission and let us work together. The final thing is, Dr. Chauhan has given 3 missions: Mission Connect, Mission Synergy, and Mission Outcome. So let us connect with each other, then it becomes force multiplier. 1 + 1 is 11 instead of just 2. So let us bring that synergy in your endeavors as well as in our endeavors. And then it brings, the outcome is important, not the output, outcome is important. So mission outcome. So let us remember these 3 missions. Let us connect with each other, bring synergy for each other's endeavors, and then that will bring fruitful outcome and make this Viksit Bharat, make our country prosperous India. Thank you so much and welcome to all, each and every one of you.
Thank you, sir, for your inspiring words and visionary leadership. It's now time to hear from our esteemed guest of honor, Dr. Umashankari Kannan, former head, Reactor Physics and Design Division, Bhabha Atomic Research Center, Mumbai, and senior professor at Homi Bhabha National Institute, Mumbai. Dr. Kannan has retired as an outstanding scientist and formerly was heading the Reactor Physics Design Division at Bhabha Atomic Research Center. Her specialization includes thorium utilization in advanced reactors, nuclear data physics, and physics of nuclear fuel cycle. She was the prime physics designer of advanced heavy water reactors with multiple fuel cycles using plutonium and low-enriched uranium as external fissile feed with thorium. She has designed several irradiation experiments for qualifying the safety of thorium-based fuels and performed studies for reprocessing of irradiated thorium fuel. Some of her other significant contributions are designs of Indian pressurized water reactors and molten salt reactors. She has been honored with Fellowship of Indian National Academy of Engineering for her pioneering work on thorium fuel cycle studies. Ma'am, I invite you for your address. Thank you.
Thank you for the kind introduction, Dr. Archana. First of all, I'm very glad to be here in this August conference. Thank you for inviting me, Professor Alpana, and Chancellor Selvamurthy sir, and then Keswan and Verde sir. A very good morning to all of you and all the dignitaries present of the stage. I would like to be brief because I was told to address like a guest of honor. So I thought I will start with general aspects because many students are also here. So first, let us talk about nuclear energy. We already know that it's a low carbon technology, but how do we quantify its performance? For example, if you see the IPCC reports or statistics, it says that the coal would produce 1 kg of carbon dioxide per kilowatt hour. This everybody knows. Similarly, natural gas produces about 470. These statistics may be a little old, maybe 2014 statistics, but still it gives you a comparison. Natural gas gives you about 470 grams of carbon dioxide per unit. But nuclear emits only 16 grams of carbon dioxide. Similarly, wind also gives you only 14. And hydel, of course, it has to be very, very low carbon technology, it gives you only 4 grams per unit. So obviously, we have to cut down on the fossil fuels. It has to be eliminated so that our next generation can inherit a cleaner earth. So now, how is the world performing with respect to nuclear energy? Only 36% of the total energy of the generated in the world is from nuclear, hydro, and solar put together. And about 61% is coming from fossil fuels. So obviously we have a very, very huge task ahead of us to increase the green share, that is changeover from coal to the green, that is nuclear and other renewable sources. So then we have to make more and more nuclear reactors. Then comes the next question, what type of nuclear reactors we have to make or we have to design and build? Today, over 70% of the reactors in the world are based on light water reactor technology. If from basic physics, you know that you can use light water, which is the simplest coolant. And if you're using light water, you have to use enriched uranium. So many countries don't have the enrichment facilities, so they go in for natural uranium and heavy water type of technology. But still, 70% of the reactors in the world, more than about 400 reactors, are based on light water reactor technology. And now Gen 4 forum of the IAEA has given some guidelines of what kind of reactors to be built in the near future, and there are some 6 different design concepts which they have given. So, but if we see it in the perspective of the carbon neutrality, we have to make several thousands of reactors. So this is not sufficient. We have to go expand our program manifold and multiply our reactors in a much more faster pace of time and a lower span of time. Also, we need nuclear energy not only for the power production, we also need it for the industrial processes, district heating, water desalination, icebreakers, data centers, medical isotopes, agriculture, almost every field we would require the nuclear energy. So the design goal now has to be focused on what type of, there is a debate going on with the experts, whether you use proven technology or we use innovative technology. So probably we'll have to have a mix of both types of reactors. Now coming to this particular conference, we have 3 major objectives when we are performing the nuclear reactor design. One is it should be safe, it should be economic, it should be reliable. We'll not talk about the economics today, we'll talk about safety and reliability. Nuclear by far is the most reliable source of energy. It's a continuous source of energy for all types of application. That's why people are going for more and more of nuclear as a power source. So now that brings us to safety and reliability. We have to design multiple systems or process systems or multiple equipments which take care of the nuclear safety to a higher order of safety, nuclear plants to higher order of safety. It has to be many times compared to what is there in the present generation reactors. Now, let me give you one small example. It may be, as the story goes, in 1942, when the first Chicago pile went critical, there was a man controlling the control rod. A control rod was tied to a rope, and there was a man standing with an axe, and when there is a signal given, he had to cut the rope. So you just imagine, there is that kind of safety only was there at that particular time. There's no regulator will allow it today. But the reliability associated with the rope, there is a reliability associated with the absorber material, there's a reliability associated with this hand, with this mind, and with the person. So this is the kind of things which we are working. That is just to show an example. But today, when you are designing equipments and process systems, you will have so much of reliability to be accounted for. And that's why the word SCRAM has come, safety, control, rod, axe, man. So that is what it was told at that time. So even today we use the term SCRAM for scramming the reactor or controlling or making the reactor protection or safely shut down. So this was some 83 years ago. Now the safety guidelines have become much more stringent. And today we are talking of several design systems. We have multiple measures of safety, multiple barriers which we have to build in. But safety alone is not enough. like Chancellor just now said, it has to be reliable. It has to reliably operate so that you can be in a safe domain. So both safety and reliability have to be proved convincingly so that the public is safe. So now with respect to safety, we have many safety measures: passive safety, that's inherent safety, but the physics processes or the phenomenological safety, which makes the reactor or the become safer even in transient situations. Then you have safe shutdown mechanisms. Shutdown and safe shutdown, both are very, very important. Then if a transient or untoward incident happens, then how do you mitigate this? Then you have an exclusion zone. So all these things are coming as part of the safety and reliability. Now, especially we are talking today about SMRs and we're talking about multiple of reactors in the same region and so on. So the objective is to make the plant boundary itself as the exclusion zone. This puts a tall order on the analysis and the design as such, so that all the radioactivity is contained within the containment itself. This is really a tall order where we have to go for very low core damage frequencies and very reliable systems. So all these subjects and topics will be covered in the next 2 days. So I'm very happy to be part of this gathering here and very happy that you have invited me here. It's an experience for me, and thank you for all the hospitality and everything. Thank you very much.
Thank you, ma'am, for sharing your valuable perspectives with us, and we look forward to your invited lecture. Now we come to one of the most awaited segments of the event, the inaugural address and the keynote talk. It is an immense honor to welcome our chief guest, Dr. D.K. Aswal, Group Director, Director, Health, Safety and Environment Group, Associate Director, Medical Group, and Director, National Radiation Emergency Response, Department of Atomic Energy, Government of India, Bhabha Atomic Research Center, Mumbai. May I please introduce our chief guest briefly? Dr. Aswal is the director of CSIR National Physical Laboratory, New Delhi since 2015, December 2015. In addition to his role as an outstanding scientist at Bhabha Atomic Research Center, he has served as Secretary of Atomic Energy Education Society, holds an MSc in Physics from Garbhal University and PhD from Mumbai University. He has conducted postdoctoral research at the Research Institute of Electronics, Hamamatsu, Japan. A renowned expert in condensed matter physics, his work includes molecular electronics, organic films, thermoelectric power generators, and gas sensors. He has published over 250 peer-reviewed papers, edited 3 books, contributed 20 book chapters, and filed patents, and secured the trademark for Bharatiya Nirdeshak Dravyas, BND, India's certified reference materials. Dr. Aswal is an active member of International Bureau of Weights and Measures, France, the Asia Pacific Meteorology Program, and the International Union of Pure and Applied Physics. May I now invite Dr. Aswal to deliver his keynote address. Thanks.
Yeah, so very good morning to all of you, and I could see there are large number of kids. I hope you have understood the reliability and safety. Understood well? Simple example is that if you have to buy an iPhone and a normal phone, which will you buy? iPhone or normal phone? iPhone, sure. Raise your hands those who want to buy iPhone. And those who want other phone. You see, there are 2 things. There can be reliability and safety, but you should have money. So I could understand that they want to buy iPhone versus money is not available, so the rest is okay. But if you have been given good amount of money, then iPhone everyone. Reason is it has got reliability and safety, both together. But don't get confused, reliability and safety. They may not be the same. For example, suppose I want to hire a driver for my car, right? Now he is well trained, he has got driving license, everything. So he is reliable from that point of view, right? So since he knows all the rules and regulations, so ideally he should be safe, right? but ऐसा होता नहीं है, वो दारू पी के बहुत तेज चलाता गाड़ी, So a reliable person can become the unsafe. Right? Yes or no? So it depends upon the scenario. So reliability, safety, and the cost. These are very, what do you call that, closely related. And therefore each part need to be looked into the independent perspective. तो जब मैं गाड़ी का ड्राइवर हायर करूंगा तो मैं ये देखूंगा दारू पीता कि नहीं पीता है, और whether he's a very heavy drinker. So these kind of things one has to, one should know about it. Right? Yeah. So what I will do, I will give you a brief presentation which you can see on your screen. And I have already explained you the reliability and safety, so I don't have to tell these definitions. You can always see. So reliability is the point is that the person, the equipment, the process should work for the time for which is meant. अगर गाड़ी मेरे को 15 साल के लिए बनी तो गाड़ी should run for 15 years without any trouble. So that is reliability and safety, Next. And I explained that the relationship between reliability and safety is little complex. So you can have a reliable system, but this can be a safer like iPhone. But then there are unsafe systems that reduces reliability. A system can be reliable but not safe. I explained the driver. And a system can be safe but not reliable. कई आदमी बहुत अच्छा है लेकिन काम नहीं करता है, बहुत रिलायबल आदमी सब करेगा लेकिन जो फंक्शन उसका है वो नहीं कर रहा है, तो इट्स सेफ बट अनरिलायबल. नेक्स्ट. Now, what is the most reliable thing in the world, in the universe, which is the sun. Sun is producing the fusion energy reliably, safely for last 4.5 billion years and will continue to produce the energy for another 5 billion years. So if you want to mimic the reliability and safety, you should see how the sun works. Do you know how sun works? कौन से प्रिंसिपल पे काम करता है सन? Fusion. So it is a fusion energy which is produced 24/7 in a reliable manner. Now the question is that, you see, the diameter of sun is roughly 14 lakh kilometers against few tens of thousands of Earth. So how it does it? So the fundamental physics is that it has got a plenty of hydrogen with it, and the hydrogen will fuse together, and as you know, E is equal to delta mc square. When the two small atoms merge, there will be a mass difference, and mass will convert to the energy, right? But remember, when you fuse together, say let us say hydrogen, when you heat it, electron will go out. So basically you have got a proton. So can you fuse two protons? Very difficult, because there is a Coulomb barrier. Proton cannot be pushed together. But sun does that. How? It produces a heat of a temperature of 15 million degrees Celsius at the core. So temperature is very high, and also the pressure is very high. So high temperature, high pressure leads to the fusion of proton, and what it emits finally? Helium. And helium is a safe. It has no radioactivity, nothing. So what sun has done is produced energy, hydrogen abundance, 4.5 billion years and another 5 billion years, absolutely no problem, and giving you only helium. Right? The next, as I said, the core temperature is 15 million degrees Celsius, and the surface is 5,000 degrees Celsius only, roughly 6,000 degrees Celsius. Core pressure is 50 million atmosphere, 4.50 billion atmosphere, and difference between this and is 10^13 atmosphere. Now one should ask this question now. If there is so high temperature in the core and so high pressure at the core, Why does it explode? What is the answer? Any answer? Answer is the gravity. So the gravity of the sun core is very, very high, roughly 30 times higher than the normal gravity. So there is a gravitation pull inside, and when the fusion takes place, the pressure outside. So there is a equilibrium pressure. So what happens if something goes unusual? So there is a large fusion energy. What will happen? The pressure will drop. The more the pressure drops, what will happen? The reaction will come down. So it's a self-regulating system. And we have not done it. It is done by the nature. Next. So as I said, a self-sustaining nature of reactions, longevity and predictability. That is, since it has got plenty of hydrogen available, so it is reliable for not for 1 to 100 years. I said it, billions of years. And stable energy output. Except the solar cycle, which comes after 11 years, the temperature at the sun surface is constant. Our global warming is taking place not because of sun, because of we have created too much of greenhouse gases like carbon dioxide and methane, which are warming up the earth. Next. And safety, as I said, it emits only helium gas and the energy. Energy is used by us, and helium is almost safe. The only problem comes when there are, and it has no radioactive element, which Dr. Kannan was saying that when you are doing a fission, you have to become very, very cautious about the fission products, which comes from uranium broken into the fission products and they become radioactive, they can be dangerous. But nature has given you that there is no long-lived radioactive nuclei. No greenhouse gases, no CO2, nothing, no methane. And only one problem comes the solar flares. Sometimes there is eruptions, but Earth has got its own magnetic system. So most of the solar flares are taken care by because they are charged particles, and charged particles are diverted by the magnetic field of the Earth. So therefore, sun for over billions of years is highly reliable and safe. Next. So the question is, and ये क्वेश्चन आपके मन में भी आना चाहिए था, फिर हम सन बना क्यों नहीं लेते हैं फिर अर्थ के ऊपर? एंड वर्ल्ड में ये सब आजकल हो रहा है. चाइना, फ्रांस, अमेरिका, दे आर वरीड अबाउट कि हम लोग कब फ्यूजन बनाएं. एंड जिस दिन हमारी फ्यूजन एनर्जी बन जाएगी, मेक श्योर दैट वी नॉट रिक्वायर एनी ऑफ अदर एनर्जी. सो द ओनली वन प्रॉब्लम, आई हैव नो प्रॉब्लम मेकिंग द सन ऑन द अर्थ. पर भाई साहब इसको मैं बॉक्स कैसे करूंगा? You have to put inside a cage now. And I said that the billions of atmosphere pressure and millions of temperature. ये भी आना चाहिए. Inside the sun, what is the advantage? There is a gravitational force. Here you don't have that if you want to create gravitational. So you have to look after the alternative to the gravitational force, number one. You have to create a huge amount of pressure and huge amount of temperature. Next. So now you have to see the physics part of it. Suppose you want to do proton-proton, that means the hydrogen-hydrogen. Easiest one, which sun does. There is called a cross-section. The cross-section for proton-proton is 10⁻⁻43. The probability of having proton-proton fusion is very, very small. But sun is lucky because it has got a plenty of hydrogen available in it. Okay, so if we do on Earth using the hydrogen, it becomes very difficult. Though it can be done only 15 million degrees temperature and very low pressure. So what is the next option? Next option is you go for the DT and DD, deuterium and tritium. So definitely deuterium and tritium, you see the blue curve. The cross section goes by 10⁻28 times higher. It becomes most probabilistic. But the unfortunate part is you have to have the 150 million degrees temperature now. Sun produces only 15 million degree temperature. We have to produce 150 million degrees Celsius on the earth. कैसे बनाएंगे भाई? तो ये क्वेश्चन है. And so what you see is that deuterium is available in the water. You produce with tritium, you make a, if you got 100 million degrees Celsius or 150 million degree temperature, you will produce a neutron, and you have a lithium back. So what you can do is this neutron can bombard on lithium and produce a tritium back. So deuterium-tritium combination is forever. If you know how to make the reactor, it is forever. The only problem is how to create a temperature of 150 million degrees Celsius and how to create that kind of pressure. And then how to box it. So if you can do these three things, fusion energy is done. But let me tell you that there are many startups, they have come up with the new ideas and which they are becoming successful. Next. So one of the things is that magnetic fusion. So what do? You create a very high temperature. What will happen at very high temperature? Gas will convert into plasma ions. And once you create a plasma, you can rotate them in a magnetic confining a magnetic field. And you apply a magnetic push inside and they can become a very high temperature. And for temperature, there are n number of methods by which you can increase the temperature of the plasma. So this is called the tokamak, and this is the one. The second is the inertial fusion, in which you put so much of laser light in a very confined place. The negative point of this is that it is only for a very small time, nanosecond time. The advantage here is that one can create a 100 second. But very recently, China has produced a temperature of 100 million degrees Celsius temperature. And their plasma has already gone for 1033 seconds. So China is very close to producing the fusion energy. And so is France. And we have got an international project called ITER. Suna hai aapne kabhi? ITER, where the India is also a partnership. So we have been contributing there, but that will come little later. But the China and France and to Korea and Japan, these are the countries they are working very hard. Next. So as I said, it's very simple. If you can create a fusion over here, the neutron comes, they come in lithium. The lithium can become very hot. You can take that heat exchanger, you can produce the power. And tritium can come back by this neutron lithium reaction. Next. So as I said, China has already produced this. This is a big news. And this is a little late. I remember yesterday they have also created a temperature of 100 million degrees Celsius temperature. Next. And same as the West is the France tokamak, which has also created this kind of things. Next. So there are certain things, machines of UK, US, Japan, you must read them. And ITER India, we have also planning of the SST Bharat. Okay, where the tokamak will come and we can some point of time, not immediately, maybe 2040, 50, somehow in India we always miss the bus because probably we don't have a appropriate leadership at the young age. And it's very important that at young age you start taking the concrete decisions. Next. So this is since I am the director of the Institute of Plasma Research, and our role is to do the plasma research and put a framework for the national policies, and this is what we have put up. So we have done a huge amount of good work at the plasma level. We know how to create a plasma, we know this, but what we didn't know that how to increase the temperature of plasma, which Japan and France has done. So now we have created a roadmap where we will consider SST Bharat, which will become almost like a east and west of France and China, and we'll be able to produce. But in my opinion, that will come only by 2040 or so. Next. So just to impress upon you, this is India's first Aditya tokamak, which has shown that we can confine the plasma. But the temperature is less, only 10,000 degrees Celsius, and the pressure is not that high. But this is completely indigenous. Then next we made the superconducting one. Next. Called the SST tokamak. Here we could get almost 1 million degrees Celsius temperature and good plasma density. Next. And since India is a part of
ITER, we have supplied components worth 10,000 crore rupees. And India is the only country in that international collaboration where our efficiency is highest, that is 86%. एक ताली तो बजा दो यार, कि तो सोए हो. Next. So where we did contribute? We contributed in the cryostat, we contributed cooling water and cryogenics, high voltage power supplies, plasma diagnostics, and many others. Next. So it became so popular that you might have seen this news. That Honorable Prime Minister, he is the first Prime Minister along with the Macron, the President of France, to visit the ITER. And this is where when he visited, and this is our IPR scientist who has given you this topic. Next. What is important is that we are ahead of time. You see, these are our 200 Indian scientists who are working there, and in the backside, this is a dome which is a weighing of 665 tons of weight. जो पूरा बनेगा रिएक्टर, उसके जो ढक्कन लगेगा, तो पूरी बॉडी हमने बना दी है peripheral. We also made a lid, but inside is not our role as of now. So that has not been done. So this lid, which consists of 65 tons, it is lying over here. And this is made by India's L&T from the technology of Institute of Plasma Research. So this is the one which we have done. Next. So as a leader, what you have to put a map. So there is called a triple product. So triple product has a N, T and tau. So N is the plasma density. So it should be as high as possible. T is the temperature of the ions. That should be as high as possible. And tau is that how long the plasma sustains. So basically to create a fusion, you require NT tau of roughly 10 to the power 22. And temperature of which I say that 150 million degrees Celsius. In terms of it will be roughly 15 Kelvin temperature. Now, what we have seen is that India is somewhere here in these two. So for next 30, 40 years, we'll go here and straight away after that we'll jump here. So by 2040-60, we should have our own fusion reactor. But for that, we will have to create our industry, again, which is reliable and safe. We have to create our manpower. They are again reliable. It should not happen that we are becoming a scientist and we do not know what to do. We don't know what our plan is. We don't know what is the quality control, quality assurance. So all those things, we should know the physics. We should know the material science behind it. Next. So, and remember, it is a very, very expensive business. For example, it is almost 2 point, you can say roughly 4 lakh crore rupees. The cost of it is 4 lakh crore rupees. China's fusion reactor is 1,66,000 crore rupees. European is 1,35,001, and which we are proposing now is 1,20,000 crore rupees. So that is the kind of money which will require. But let me tell you, in India, this money is not a big money. If you can demonstrate the technology, Adani's, Ambani's, Tata's are ready with giving the 1 lakh crore rupees. Absolutely no problem. Fortunately, in your era, India is such a country where money is not a constant at all. What is a constant at all is our reliability and safety. Next. So, as we know that we are in the modern timer. Russia, America, what they have done, they made a small reactor, this is a small tokamak, then bigger one, then bigger one, then bigger one. Many people they ask, how we are going to jump straight to the bigger one. Finally, nowadays the machine learning, deep learning has become so powerful that you can create a virtual images. You can create a virtual digital twins. So, we have already started to work on the digital twins. So, as I said, we have got Aditya, and using Aditya, we have already started creating a digital twins. So, in the virtual machine, you can do all the operations which you can mimic in the real ones. We have got SST1, we have started creating the digital twin of SST1. Whatever we do, we can simulate there. And therefore, we can straight away go for the SST Bharat. It will take 5 to 10 years or 15 years for making a digital twin. But once we create a digital twin, fabrication of real experiment will become easier. And meantime, we can ask for our money, we can ask for our land, we can ask for our approvals. And the biggest point with the fusion reaction is that it does not require any major regulatory approvals because it does not contain much of the radioactivity. Next. So this I have always showed you. The China, Germany, South Korea, and UK and USA, they have got their own big programs. Everybody is following that. Next. So the conclusion is that, is India ready for the fusion energy? In my opinion, the answer is yes. Answer is yes because we have got a scientific expertise. The reliability factor is there. We have produced our fission energy nuclear reactors which are running very successfully. 700 PSWR is our indigenous technology. So we are capable, our young people are capable. Industry partnership, as I said, that L&T has given that biggest dome to the ITER. We are the one of the best performers in the ITER international program. Key challenges, of course, we need a good policy support. Private sector investment is required, but as I said that if you have got a good design, you are very sure of that, money is not a problem. Future outlook is a very, very positive, and if you youngsters are ignited, the fusion program of India will be sure shot. So thank you very much. Yeah, so if you have got any question, doubt, yeah.
I've got a question. Yeah. So when we consider RTGs, which are radioisotopic thermoelectric generators, and we compare them to nuclear fission and fusion in the current time, so based on the reliability, safety, and the economic factors, is it a better choice, or should we strive more and try to set up more of nuclear reactors than these?
You see, RTGs are altogether different. You see, in RTG, you have got a thermoelectric pile, you put a source, and that becomes a battery. This is for small powers. Okay, and those are used in space missions. Okay, so definitely you should use them and people are using them. But that small power is not required in the country, in the daily life, mobile phone or this one, so they are not required. So the application of RTs are entirely in the different domains. And they will continue to be operated, but they will never ever come in the public domain. The only small part comes in like a pacemaker, which is put in the heart. So that is done.
Thank you.
Yeah. Any other question? So are you sure the fusion will come for India? Yes or no? अरे जोर से बोलो ना यार. हाँ ठीक है. Thank you. Yeah. One more question.
Sir,
Yeah. Let him ask and then after that.
Sir, I would like to ask, and how could the
So keep mic closer.
how could the fusion energy power our space exploration missions of the future?
No, what?
How could the fusion energy particularly could empower our the space exploration missions of future?
See, once the energy is produced, you can use wherever you want to use it. Okay. Once you know how to make it power, then that can use anywhere. Power is independent of application. You have to design the power setup as per the applications. Right. So the point which I am trying to say, and the world is looking at the fusion energy because it is a very, very safe. It is mimicking the nature. And Dr. Selvam is asking, is it possible to the cold fusion? There have been a talk long time that can you do close fusion? In my opinion, that is a very tough challenge. And if at all it happens, it will be at the microwatt or milliwatt level. So that kind of things are not going to work for us.
Sir, I also have one. Basically, don't have the question, but as young students are sitting, they are 12th, 11th, 12th student. So I would like to request you if you can give some direction how they can proceed further in their future, and about they would like to learn about CERN, ITER, and our GSI, how they can go for internship and they can do research there.
So this is a little broader scientific question. As India is progressing our science and technology department is also progressing. The policy have been changed. Now we have got the Anusandhan NRF. Have you heard of that? National Research Foundation. Okay. So Anusandhan NRF is a central agency which is supporting almost all universities now and students, their fellowships, postdoc fellowships, higher educations, trips abroad if you want to attend some conferences. So one can go to the ANRF website and see that what they can do. So that is at the national level. At department wise, you have a large number of scientific departments in the country. So let me start with the Ministry of Science and Technology, Department of Science and Technology. You have got a DBT, Biology if you want to do, Department of Biotechnology. You have got the CSIR, Scientific Council of Scientific and Industrial Research, where you can do the research towards the industry. Then you have got the Ministry of Earth Sciences if you want to investigate about the atmospheres of the earth, water, soil, whatever you want to do. Then you have got Department of Atomic Energy, which is dealing with the fission energy. Largely we have successful. Fusion energy, we have taken up the role, which I have given you the lecture. Then you have a Department of Space. Now and then you hear that they launch rockets and this and that. Then you have got a great department, DRDO. Okay. And most of the places you have got intake at entry level. If you are good at your subject, say for example, when I was just 21 years old, just finished my MSc, I went for the first time Mumbai and got selected. Only thing what you have to keep is you have to keep your concepts very clean. What you understand should be scientifically correct. And once you have got that, you can be selected in any of the competitions. So DRC conducts every year called the OCES course after your MSc. And roughly the ad comes in the month of January. Those who have done BSc, MSc in first class, and engineering, any discipline, almost all disciplines, BTech and DE. January ad comes, somewhere in May, June, you will have the written exam, and by August, you will have interviewed and you are selected as a scientist there. Now, typically 1 lakh applicants are there. After written exam, 3,000 are selected, and after 3,000, through interview, roughly 200 are selected. So the probability of getting you selected becomes less than 1%. But 1% chances are very large. If you become a good scholar, you understand science and technology the way they are. Similarly, ISRO has got a program, DRDO has got a program, CSR has got, there are so many laboratories, they have got a program. So there are plenty of job opportunities if you put all together. So suppose you are not able to get a permanent job, what next? You can go to the PhD programs. There are large number of PhD programs, fellowships given. After PhD, you can go for the postdoctoral fellowship. You can go abroad. You can go university. You can have this one. So India has got a large opportunities in science and technologies. And the new generation, they are not looking for a government job nowadays. They are looking for their startups. You see, the fusion one, there are large number of young entrepreneurs. They have found this kind of fusion at a very small level. It is only the scaling up later. So there are many groups in the world where the young, in fact, one fusion was demonstrated by just 12-year boy in US. Okay, he understood and he did it at a very small level. And after when he demonstrated, when he said that the neutrons are coming to the fusion, so he is being given a huge amount of funds. So if you have got ideas, money is not a criteria in the country, but you have to hit the right science and technology. Yeah. Okay, thank you.
Can we have a huge round of applause for our guests? Thank you, sir, for the enlightening and thought-provoking keynote address and sharing your profound insights with us. At this moment, we take pleasure in honoring our esteemed dignitaries, and I invite Honorable President ASTIF, Dr. W. Selva-Murthy, Professor Dr. Alpna Goel, Professor Dr. P.V. Barde, to felicitate our chief guest, Dr. D.K. Aswal, Group Director, Bhabha Atomic Research Center. Further, I request Sir and Madam to felicitate Dr. Uma Shankari Kannan, our guest of honor. Thank you, sir. Thank you, ma'am. I request Professor Goel and Professor Barde to kindly felicitate Dr. W. Selva-Murthy, President ASTIF. Thank you to all. To formally conclude this inaugural session, I would now like to deliver the vote of thanks. Honorable dignitaries, esteemed experts, industry leaders, distinguished guests, senior officials of Amity University, participants, and dear students, it's my privilege to extend a heartfelt vote of thanks on this special occasion. First and foremost, I express my sincere gratitude to our senior leadership and higher officials for their visionary guidance and unwavering support. Their commitment to excellence has been instrumental in shaping such impactful initiatives. A special note of appreciation to our esteemed Chancellor, sir, for his constant encouragement and support in fostering developmental activities. I also extend my deep gratitude to our Vice Chancellor, Madam, whose steadfast guidance have been invaluable for us. A special thanks to our President ASTIF for his unwavering support and guidance throughout. On behalf of AINST and the entire organizing team, I extend a sincere thanks to all the delegates, guest speakers, and subject matter experts. Your presence and valuable insights have greatly enriched this event. I also express my gratitude to the participants who have traveled from distant locations to attend this conference. Your engagement and enthusiasm will add immense value. A heartfelt thanks to Dr. D.K. Aswal, Group Director at BRC, for his inspiring address, which has been a source of motivation to all of us. Thankful to Dr. Uma Shankari Kannan for her insightful words. We are grateful to both of you, sir and ma'am, for joining us. Our deep appreciation goes to the industry partners and sponsors, Thermo Fisher Scientific, Advanced Tech Controls, Saru Shielding, Ortec Amitech, and Atomic Energy Regulatory Board for their trust and support in making this event possible. Thank you to the publishing partners, Finger Nature, for taking out the proceedings. I extend my sincere gratitude to our director and head for her encouragement, guidance, and unwavering support. Special thanks to Professor Barde for his trust in us and invaluable expertise that he has been providing for organizing this conference. Congratulations to each of the dedicated members of the organizing team for their hard work and commitment. I express my sincere appreciation to all the senior faculty members and experts who have been providing their valuable suggestions, guidance throughout the planning of this conference. Without them, this wouldn't have been possible. And I extend a heartfelt gratitude to the senior officials of administration, department, Amity University, for meticulous arrangements regarding infrastructure, guest house, catering, and ensuring a smooth execution of this event. Thank you all for your participation, and I wish you a productive and insightful time ahead. Before we formally move out of this hall, we would also like to felicitate two of our guests who have joined from Bhabha Atomic Research Center. Shri R.K. Yadav, Section Head, Radiation Safety Systems Division, Bhabha Atomic Research Center. Shri R.B. Ojha, Division Head, Radiation Safety Systems Division, Bhabha Atomic Research Center. Thank you, everyone. Please join us for high tea, which will be served outside this venue. And we shall reconvene back after 12 minutes for the session. Thank you so much.